Hey, good afternoon, everybody. My name is Rob, like Smriti mentioned, and I work with the CUDA team here at NVIDIA. And today I have kind of the daunting task of condensing all of the work that's happening in CUDA into about a 30-minute presentation for you. So if you remember anything, it's that I love talking about CUDA, and you can always grab me or my coworkers in the hall. We'll talk your ear off about this stuff for hours. Otherwise, if there's one or two things that pique your interest here, my mission is done. So CUDA 13 is our latest release. It came out in August of this year. And this is really the first release that's full bore on Blackwell. We've got full support for all of the architectures and so on. But many of you know that CUDA follows semantic versioning. And so for us, going to a new major version is a really major event, and it's a significant milestone. It lets us make changes to the ABI, changes that really set the stage and lay the foundation for all the development work that we're going to do over the rest of the CUDA release. Generally speaking, a CUDA release tends to last you around 18 months or so. And so CUDA 13 for us is more than just the specific set of new things that are in the box. It's really about how we carry forward the CUDA programming model and some of the really exciting things that we're doing over the next 6 to 12 months even. Before I get into all the really exciting stuff, though, let me kind of paint a picture for you for what's in the box with CUDA 13 itself. Memory management is always a really significant part of optimization for any algorithm. And this is independent of architecture. This could be a traditional ARM server topology. It could be Grace. It could be x86 PCIe. It could be an embedded system. It doesn't really matter. The point is that in any system, where your memory is, when it's moving and when it's accessed, is one of the most critical pieces of information for you as a developer to be aware of. To access it on the GPU, it needs to be in GPU memory. To access it on the CPU, it needs to be in CPU memory. Otherwise, you're moving it back and forth. And so we're putting a lot of effort into extending and augmenting CUDA's memory management APIs. In CUDA 13, we've given you support for things like managed memory discard and UVM. We're also giving you things like the ability to pass in parameters when you call memory allocators. You can tell the runtime, I want this memory on the CPU. I want it on the GPU. I want it moved here or there. All kinds of additional hinting to control where things are moving in your system and how they're accessed. We've also added a new driver mode along the same lines called CDMM, or Compute Device Memory Manager. What this does, if you're familiar with Grace systems, the memory layouts of the Grace system were done as NUMA nodes. Each GPU represented a specific NUMA node. All the system was available in a large NUMA pool. And this is great for some types of applications. It's not as great for other kinds of applications. In particular, some of the things like Kubernetes had a little bit of a challenging time understanding NUMA and understanding where to allocate memory and where to move it around. So ultimately, what we're doing with CDMM is giving you the option to use NUMA or not. By enabling CDMM, you still can take advantage of all the coherency in the Grace platforms. You can still use ATS and so on, but you don't have a NUMA-style topology. You have a much more traditional memory-style topology. So if you're taking legacy applications and bringing them in, or if you have other things that are not familiar with NUMA, this can be a great way. Ultimately, we're just giving you more flexibility in how you configure these systems and how you use the memory that's available to you. For Windows users and Windows developers, we're now signing all of the executables and libraries that we distribute, which is great if you're trying to comply with particular security requirements or if you're trying to sell through particular OEMs and things like this. We've augmented our checkpoint and restore. Now you can migrate to different GPUs and different platforms. Now, some of you may not be familiar with checkpoint and restore. There are two real important use cases for this. One is if you have a really long-running job. Let's say you're doing a ML training or something like this that can take many hours or days. It's nice to be able to periodically checkpoint it so that if something happens to the system, you get a single event upset or get some unrecoverable error, you need to resume, you can do that. The other really nice thing about checkpointing and restoring is inference. And what makes it nice for inference is that if you've ever tried to cold start an inference system, you can understand that doing all the initial setup and configuration and so on can take a non-negligible amount of time. And there are actually some recent publications where people have been using GPU checkpointing and restore for warm start of inference systems. And you can get some really substantial speedups at system configuration or initialization time by restoring from a checkpoint as opposed to launching a new cold application and having that application go through all of its initial setup. There are some other kind of nerdy things in here that I'm really fond of. For example, we can spill registers out of individual kernels to shared memory. This is representative of a long list of things that you can do at the optimization level. It's really kind of a micro optimization, but the nice thing here is that you can get about an order of magnitude lower latency by spilling to shared memory than you can with traditional register spilling. So again, this is like, I'm not going to go into a lot of detail about this because it's a very niche thing and it's a very ninja level optimization, but we have a lot of stuff in the box that are like this. And then another big one that I'll come back to is a unification of the programming model and of the development architecture between our embedded SoC targets, the Jetson family, and our server topologies in the data center. Historically, NVIDIA has had these treated as two separate entities effectively for software developers. And now with updates to the driver and updates to the toolkit, these are really one and the same. You can write one application, run it anywhere, scale it all the way from a massive cluster scale data center down to a robot. So really cool things. And in terms of our long-term development directions, these are probably about the same as when I had come and spoken to you last year. In terms of languages, our goal within CUDA is always to be present wherever you want to be developing. So CUDA has a long pedigree in C++. It grew up there. It's been used there for a long time. Python, of course, extremely popular and relevant in many different domains, HPC, deep learning, and so on. We've put a lot of effort and continue to put a lot of effort into migrating the stack to Python, making Python a first-class language for CUDA Toolkit. And that doesn't mean writing C++ in Python. It really means reinterpreting and reimagining how you write and build applications to take advantage of Python natively. We're also looking at additional languages that are becoming more prevalent, things like Rust, C#, other areas. Ultimately, again, this is something where we want to be present and available. We don't want you to have to take a C++.so and put a wrapper around it, integrate it with some toolkit or framework. We want you to just be able to use CUDA the way Mother Nature intended effectively. Now, NVIDIA talks a lot about scaling, right? Scale up, scale down, scale out, scale everywhere. And it's great to build large-scale clusters. If anyone has ever done programming for large-scale clusters, it can be a little bit more challenging. Now, the technologies to do this aren't really new, right? MPI is not new. It's been around for a long time. There are lots of things that make it easier and better. But we're always putting a lot of effort and energy into trying to understand how we can do this more effectively. How can we give you tools that allow you to build at cluster scale, run inference at cluster scale, calculate workloads at cluster scale, without having to understand the nuances and the mechanics of working in a cluster? We have things that we've already come out with, like CuPy numeric, that allow you to do this kind of scaling. Take NumPy-like code and broadcast it across a wide variety of machines. We also are working on new programming models where you can take things like a CUDA graph and then selectively distribute memory allocations, workload elements, and so on across the entirety of a cluster. So in general, we're putting a lot of work into trying to make cluster scale orchestration and application management much easier for you. The flip side of that is hierarchy and locality. It's kind of turtles all the way down. If you're looking at cluster scale, if you're looking at a single server system with multiple GPUs, if you're looking at a single GPU, the concepts repeat. Moving memory is expensive. It's always expensive. What changes is the cost, but it's always orders of magnitude slower to access global memory than it is to access on-chip memory. It's orders of magnitude slower to copy from a CPU to a GPU. It doesn't matter what hardware topology you're on. That's just fundamental limitations of the architectures that exist in the world today. And so I mentioned earlier some of the kind of small scale improvements, but this is in aggregate a big push from us to help make memory management easier and to make the migration of memory more transparent, more seamless, and more predictable. You want to understand where your data is moving and when. You want to understand why. And when you're doing system level optimization, this is one of the real pieces of low-hanging fruit. Like, when is my data moving? And what am I spending in terms of energy? What am I spending in terms of time? How can I reduce it and orchestrate? Now, on a completely different note, we have a topology that's becoming much more prevalent. If you saw the keynote yesterday, you heard Jensen talking about aerial, you heard Jensen talking about quantum computing. You've probably done some sessions about this too. All of these domains have something in common, which is that we have to respond to real world events very, very quickly. You're talking about RAN applications, for instance. You have windows of data processing on the order of hundreds of microseconds. If you're talking about quantum computing, you have windows on the order of tens of microseconds. And if your GPU or your system is not able to respond in that time frame, tough luck, you've lost it. And so being able to schedule things on the GPU, being able to predictably schedule things on the GPU with deterministic latency in response to real world events outside of the GPU system is critically important. And the GPUs and the GPU software wasn't, if you think back to like 30 years ago when we were doing Virtual Fighter, it wasn't designed for that. If it takes a couple extra milliseconds to render a frame, like, that's a bummer, but it doesn't cost you anything really in the real world. If any of the domain applications I mentioned and a bunch of other ones besides, it really does. And so there's a lot that we're doing in terms of how we can schedule these workloads, how we can orchestrate, and just in general, how we can be responsive to external events. I'm not going to talk about it much today, but if this is something that interests you, find me afterwards. I'm happy to talk about this because it's really exciting. GPU scheduling is one of those things that I get very excited about. I'm probably unique. But anyway, it's very, very important for a lot of different domains, and the way that we control and the way we orchestrate is super important. And finally, the last one for us before I really get into the meat of this is just generally how we educate people about the platform. All of this is complex. We try to make it as easy as possible. One of the things we always like to say is that we try to write 1 million lines of code so you only have to write one. But we all know that's a lie, right? You have to write a lot of code. And understanding how to write that code and what the system is doing under the hood and how to use the hardware that you have to maximal advantage is hard. CUDA as a platform has grown really organically over the last 20 years. And the documentation and the examples and everything have kind of grown organically with it. And coming to it fresh, I like to tell a story. Many of you probably know Stephen Jones, or at least you've seen him speak at other GTC events or on YouTube or what have you. And before I joined NVIDIA, I had a couple of weeks to myself. And so I sat down and I did a bunch of programming exercises on the GPU. I thought, I'm going to do a reduction or a scan or, pick any kind of like basic algorithm, right? So I did it and I got my performance to a pretty good point. I was really happy with it. And then I went and joined NVIDIA and I said, hey, Stephen Jones's desk is right across the hall. I'm going to go ask him how well I did. And he took a look at my code and he said, no, this is terrible. This is wrong, this is wrong, this is wrong. You should have used that over here. And I was thinking to myself, how would I learn that outside of NVIDIA? Everyone in this room can't go and stand on Stephen's desk and annoy him until he looks at your code. So how do you pick this up? And so long story short, we're doing a lot to revamp the onboarding material. Completely rewriting the samples. We have an update to the programming guide where it's being completely rewritten, hopefully much easier. We have the Accelerated Computing Hub now, which is a great GitHub resource. You can, one click of a button, you're in Google Colab. You can play with things and evaluate. We're working with the DLI team to improve the courses. And my goal, anyway, is to make it so that if you as a developer want to learn CUDA, you want to teach CUDA to yourself, if you want to pick up a new technique or a new technology, whatever it is, we want to make that available and accessible to you. And so we've got a whole team of people now who are focused on this. They've actually been focused on it for about a year. The initial fruits of their labor are going to be coming public in about a month. And then beyond that, with every new release, you'll see more and more of this from us. But in general, we just need to make this much easier. Speaking of making things easier, let me get into some of the exciting things. And this is actually a project that I've been working on for about 2 years now, and I'm really, really excited about it. Because with CUDA, one of the kind of traditionally challenging things is just wrapping your head around how the GPU works. Parallel programming is inherently a little bit like seeing into the fourth dimension. And you have to understand how to segment work across the SMs, how to get thousands and thousands of threads cooperating with one another in parallel. And for many, many domains, that's not really what you want to do. You want to do the dot product of a tensor with another tensor, or do a block multiplied by a scalar, or add, or whatever. You're just trying to do some math, basically. And so the programming model that allows you to do that most effectively is probably something that looks a lot like NumPy. I can have an array of data. I can take the dot product with another array of data. And I don't necessarily want to understand or know how to deep dive into the internal machinations of the GPU to make all that happen. It's much more natural to just express the math at the array or the tensor level. There's another problem that kind of crops up in parallel with this, which is that as we go from GPU generation to GPU generation, the tensor cores become much more capable and much more complex as a result. We now have many different data types. We have many different possible combinations of memory accesses and data types and tile sizes and so on. And that did a couple of things. First, it made a lot of the libraries very, very large. If you look at cuBLAS, cuDNN, the historical way of doing these things has been to have tens or hundreds of thousands of discrete kernels for any possible combination of data type, problem shape, what have you. The other thing it did is make things architecture specific. If you think back to the early days of GPUs and up until really about Ampere, we had a technology that many of you have probably heard about called PTX. PTX is a virtual ISA assembly language. And the way that we always handled portability was that when a new GPU generation came out, we have compilers that could take that virtual ISA assembly language, translate it into the specific operations that run on that GPU, and then get them on the hardware. That works really well for JIT compiling one instruction to another instruction or a set of instructions to another set. It doesn't really work well if your application has to fundamentally change. And that's what happens with this domain-specific hardware. Going from an Ampere-era tensor core, for instance, it required a single warp of 32 threads to fully drive the tensor core. On Hopper, that same tensor core now requires 128 threads across 4 warps to drive it effectively. And we can JIT compile instructions to other instructions, but we can't JIT compile new threads into existence. We can't JIT compile a new memory layout for you. And so we started to think about how far do you need to zoom out to be able to regain that independence and that portability between GPU generations. And it turns out that you pretty much have to zoom out to the same level I was just talking about. So we can kind of kill 2 birds with one stone. We can give you as developers a much more performant and productive programming model that's easier to use, easier to teach people, easier to understand, and that reintroduces portability to different GPU architectures and generations by leaning into and really relying more on runtime code generation. It's not thousands and thousands and thousands of precompiled, pre-built kernels. It's the compiler understanding the underlying hardware and mapping abstracted algorithmic operations onto that hardware for maximal effect. And so the programming model looks a lot like this. If you think about the way that we usually subdivide work on GPUs, you have the grid of data that represents the entirety of your problem space. You subdivided that into blocks. Each block represented something that was going to run on an individual SM. And then in the traditional SMT model, you're further subdividing it into threads. And those threads have to communicate with one another and handshake and do all the things that threads do. In the tile model, you're not doing that last step. You're just subdividing your work into individual blocks and then describing things that are going to happen to those blocks. Each unit of data is a tile, not a specific element. And you're doing things at the array level of granularity. Now, of course, not your entire application is built this way. You have things that are element-wise. You have things that are not array or block level operations. And so we expect that all of this fits into a much larger ecosystem. I've got this one circled here on the slide. CUTile is our user-facing programming model expression of this. And that's an asterisk I'll come back to in a second. But ultimately, this sits side by side with SMT programming, with some of the more low-level optimizations like Cutlass. And it's really a pick the right tool for the right job. All of these things compose well into the same program. You have SMT kernels that are doing traditional things. We're not saying you need to rewrite your whole application in Tile, but for things that can take advantage of Tile, or especially things that are more linear algebra based or would make good use of the tensor cores, write them in Tile. If you really want to get into the low levels and kind of hand tweak and optimize things, we have lower level expressions of the same thing in Cutlass. The big difference between Tile and Cutlass, and I'll mention this quickly because I get this question a lot, is what's the difference? They're both kind of solving the same problem. How do I drive the tensor cores from a higher level language? Cutlass is all about exposing the low-level internals of the GPU at architecture-specific granularity. Tile is about getting good performance on a GPU with architecture-agnostic granularity. So what that means is that if you really want to do something that's non-portable, Cutlass exposes it to you, and Tile doesn't. Now, the good thing about this is that for most use cases, architecture independence isn't something that you have to give up. You can get very, very close to the speed of light on a GPU architecture with CUDA. If you want to go the extra mile and really optimize it beyond that, Cutlass is available to you. The trade-off is that it's not going to be portable. So you kind of want to pick the smallest subset of your application to write in there as you possibly can. But in general, all of these things are routes to the same place, which is maximal performance on the GPU. Just to give you a kind of quick feel for how this looks, I've got 3 algorithms here on the screen, or rather I should say 3 different variants of the same algorithm. On the left, I'm showing a SMT matrix multiply written in Python and using Numba to compile it. And for anyone who's done matrix multiplication, this is like the worst possible implementation of matrix multiplication. It's not driving the GPU to maximal efficiency at all. But it is kind of long and it's fairly complex, right? We have to take the matrix multiplication operation, we have to divide it into individual threads, figure out how they communicate with one another, all that fun stuff. The 2 green boxes show the same matrix multiplication, making full use of the tensor cores, driving the GPU in top gear with the pedal all the way down in significantly less code. And that's the Tile programming model in a nutshell. We're able to do very, very high performance operations at an abstracted level of granularity in a really intuitive and productive programming model. And this is especially intuitive for anyone who's worked with NumPy. In the Python space especially, we've really intentionally designed the API to look and feel very intuitive to people who have done array and tensor-level programming before. The C++ version of it looks very similar. Obviously, C++ has different syntax and different semantics, but by and large, the way that you express tile operations, the way that you express these linear algebra operations in C++ is pretty much the same. We also have full support for profiling and debugging and so on in inside systems. I'll just show you this very quickly. We have statistics available for tile kernels. You can kind of get good summaries of how the compiler is implementing things, how the GPU is running things, and so on. We also, in 13.1, I should have mentioned, by the way, that this is all coming in 13.1 in about a month. We have source code mappings of performance metrics for tile kernels. So you can see, just as you can see for C++ today, you can see how things are breaking down, how individual instructions map to particular GPU operations, and you basically get enough insight into how things are running in the system to be able to make intelligent decisions about further optimizations or just general coding. So the kind of TLDR here is that all of this stuff is expressed in Insight the way that you would expect it to be expressed in Insight, and the goal is to make it as easy to use as possible. This is all fully part of the CUDA programming model. Tile kernels or CUDA kernels, you can do all the things with tile kernels that you can do with regular kernels. You can put them in a graph. You can call them from other kernels. You know, anything you want to do with a CUDA kernel, you can do it with a tile kernel too. The other kind of interesting corollary to this is that when we look at compilation stacks, compilation doesn't just happen at the lowest level anymore. As more and more frameworks are leaning into runtime code generation and code reuse, you get a lot of things like JAX or PyTorch Inductor or these different technologies that are generating code all the way down. And so you don't just have one compiler anymore. In a real application today, especially a deep learning application, it may not be uncommon to have 5 or 10 different compilers doing different things. And so the big open question really is, how do they all work together and how do we orchestrate all this? The backend for tile programming is a model that we're calling CUDA Tile IR. And effectively, it's a parallel programming path or a parallel compilation pathway to what you had in SMPTE. Up at the top here, you can see all the kind of higher level exposures and expressions. But as we get to tile, we have a little bit of a bifurcation. On the SMPTE path, you're continuing down the way that compilation has always worked. You're going through NVCC and you're getting into the back end of NVCC, which is NVVM or kind of a variant of LLVM that generates PTX. That PTX is compiled and so on. On the right, we have a kind of conceptually equivalent parallel path where you have a tile application. That tile application goes down its own programming and compilation path. The end result of that is tile IR, which is a kind of sister to PTX, if you like. And then that at runtime is compiled down to something that actually runs on the GPU. And the way that that works is through MLIR. It's a series of lowering passes. If you're familiar with how MLIR works, we have a intermediate representation of what your algorithm is supposed to be and supposed to look like. That's compiled at runtime down to the specific sequence of instructions that runs on the GPU. And of course, this all kind of mixes and matches and plays nicely together. So every level of the stack is calling this. Many levels of the stack are generating many different things. And the end result is a binary object that is portable, that runs at performance on the GPU. Really, this part is probably only interesting if you're a compiler developer, except it gives us a really nice party trick. If you look at the way that code generation is done in the ecosystem today, and I'll use OpenAI Triton as an example here. If you write a Triton application, or if you have a higher level DSL that generates Triton, for instance, PyTorch will generate Triton, which generates other things and so on. As you go down the stack, the compilation path looks very similar. Triton generates something called Triton Tile IR, which is an MLIR dialect. It goes through a series of lowering passes and eventually winds up at the open source NVIDIA GPU backend. This is something where NVIDIA works with the OpenAI team. We contribute knowledge about the GPU architecture, specific recipes for doing different operations on that GPU, and so on. A lot of the programming and integration and coding work comes from outside of this. But end of the day, you still wind up down here. You wind up in the backend LLVM stack, and Tile works very similarly, right? If you think about how this comes together, you can have that same PyTorch application generating CUTile instead of Triton, going through the own parallel compilation path and getting onto the GPU, which sounds like we're looking at a situation where you're choosing one or the other, but actually much, much nicer than that. Because what you do instead, because this is all MLIR, and MLIR is kind of like playing with Lego for compiler people, we can take Triton tile IR, go through a dialect that translates it to NVIDIA's backend, go through the tile IR backend layers, go through the compilation flow, and get onto the GPU. And this way, NVIDIA can raise all the boats, right? If you're using Triton, remain in Triton, you can take advantage of the backend compiler, you can get the performance associated with that, you can get day zero support for new GPU architectures as they come out, get the portability, get your name on a wall. Wait, that's different. But you get all kinds of stuff as part of this for free, effectively, with backend plugins to not just Triton, but lots of different compilation frameworks and different tools. Our goal generally is to make the backend IR something that NVIDIA maintains, and then the front end and the front-facing pieces of this can be consumed by really anyone to integrate into whatever you want. And so you can imagine all kinds of DSLs for different applications that are taking advantage of optimized linear algebra for GPUs. So I'm really excited about that. Beyond that, we've got a lot of things happening. On the library side, FP64 and FP32 and larger data types are really, really important for lots of different domains. Finance, high-performance computing, you name it. GPUs are not historically super good at very, very wide computations, at least not compared to the lower precision computations that we're doing on modern GPUs. Deep learning in particular is pushing tensor cores to lower and lower precisions as opposed to more bits. That's led to a lot of research in the space, and researchers have identified techniques for doing higher precision operations with lower precision intermediate products, recovering the full accuracy and getting higher performance at the same time. And you'll sometimes hear this referred to as the Ozaki technique, and it goes by other names as well. There are a number of papers on this that have come out over the last couple of years. I have some links on the bottom of the slide here. But the TLDR is that if you look at this chart, using emulation techniques on modern GPUs, and this is on GB200 where the numbers actually came from, you're seeing very, very substantial speedups versus just out-of-the-box naive FP32, FP64 implementations, and even on lower precisions as well by using the same kind of decomposition techniques. And so this is something that we're really leaning into at the programming model layer, both for the math libraries, where you'll see this available as opt-in right now, and we're probably going to transition to it as default pretty soon in the future, as well as just for general SM programming. You can imagine Ozaki kind of data types in CCTL and things like this, where you can take advantage of emulation techniques without going through the tensor cores as well. It was released for the first time on FP32 back in 12.9, which is in May of this year. Double Precision came out with CUDA 13 Update 2. And like I said, it's opt-in right now. We do see pretty substantial benefit from this, though. So once we've given a little bit of soak time and kind of let it sink in a little bit, future releases are going to invert this. It'll become opt-in by default, and you can opt out of it if you so choose for any reason. Moving on to the compilers, I've talked a lot about runtime compilation and runtime code generation. How are we going to generate all this code? How are we going to runtime compile and finalize the GPU architectures? And ultimately, that kind of shifts the problem around a little bit, right? We're not giving you these really, really massive libraries of precompiled kernels anymore, but now we're runtime compiling something that's going to run on the GPU. And so we're putting a lot of effort into how we can make these things faster and more efficient. We've added a tool called Compile Time Advisor that analyzes your compilation flow, and you can see a nice flame chart of where the compiler is spending its time, gives you some feedback about how and where and why you can optimize things for faster compilation. We also give you more knobs you can tune to get faster compile time. So we actually have compile time focused optimizations as opposed to code efficiency implementations. This is the fast compile flag, and you can sort of choose different set points along this curve. We've also added better support, and we'll continue to improve support for runtime compilation caching of intermediate products. Right? You were always able to do this with just general JIT compilation. Now we've added caching to NVRTC as well. We're also continuing to improve and expand on the Insight tools. And my colleague Jackson is around here somewhere from the Insight team. He would love to talk to you all day about developer tools and what's going on. But in addition to the stuff we're doing for Tile, we're giving you much better Python support generally with the developer tools. And then this is a really exciting one for us. we're really leaning into LLM-based assistance here, because if you've ever used something like Insight Compute, you've probably seen that it gives you just page after page after page of statistics. And unless you've been doing GPU programming for a long time, you kind of look at it and go like, I don't know what any of this means, right? I've got all these numbers, but how do I actually fix my kernel? Well, our LLM assistant here is there to do exactly that. It'll look at your results. You can ask questions about it. You can ask it, how do I better interpret things? And how can I just generally get better performance out of the kernels based on the feedback that I've got right now? Calling back to the beginning of the presentation, I mentioned that we're unifying the compilation pathway between the data center and the embedded devices. And this is a really exciting one for us, because if you've ever done embedded development for NVIDIA, there was always a disconnect in the delta. The CUDA version might be slightly behind. You were missing some functionality. There was a different driver with different models, and it just kind of got a little bit weird. Even in the cases where it wasn't, if you were trying to write one application and run it anywhere, we just didn't give you the ability to do that. If you were building for a ARM data center system, you had a different set of libraries, you had a different set of compilers, you had a different set of everything, even though the compilers for the embedded space were largely the same. It's the same CPU architecture. They have the same instructions for the most part. There's really not a substantial technical underlying reason that they should be different. And so long story short is that they're not. And that gives us a lot of really great stuff. I'm not going to go into detail on the hardware architecture. We have other sessions here at GTC where you can learn more about this and find out more about what's going on in the embedded space and with some of the embedded products. But the key takeaway for me is that it's always been really kind of painful for me that CUDA was different in the embedded space, and now it's not. And so with 13, you get all kinds of things in the embedded space that you never had available before. In particular, scheduling assistance. And I talked about how important it is to be able to process and capture and run on real-world data without losing it. Where is that more true than in a robot? And so we give you all the scheduling tools that exist in the data center space on embedded now. You have multi-instance GPU or MIG that allows you to subdivide your GPU into physically discrete instances that don't share memory bandwidth. They can't step on one another. You get much better safety that way and more determinism, better QoS, all these good things. We give you multi-process server, MPS, which allows you to put more applications onto the GPU at the same time, get better resources utilized, really just squeeze more juice out of the thing. And then a new technology that you may have heard a little bit about, we've been talking about this for a little while now, called Green Context. Green Context takes the conceptual GPU sharing of MPS, but it does it within a particular CUDA context. It squeezes things down, gives you better spatial partitioning on the GPU, and just in general, this is where the really cool box of tricks is. But when you're trying to squeeze that last little bit of performance out of the GPU, or where you're trying to hit those really tight latency targets. But the important thing is that it's now one platform everywhere. We have one GPU driver that spans across the entire suite of products. It gives you a productivity boost. You can build on Spark, deploy on a robot, deploy on a supercomputer. It doesn't really matter. Just build wherever you want to, run it wherever you want to. It's the same now. And for me, that's very, very exciting. Confidential computing, I'll talk about it very briefly. Confidential computing is not new for us, but we do continue to improve and expand upon it. Basically what confidential computing is, if you're not familiar with it, or if you haven't heard about it, it's a system technique for protecting your data while it's in use. There are really good techniques for protecting data while it's in transit across the network. There are really good techniques for protecting the data while it's sitting on your hard drive. When it's in flight to the GPU and is being operated on within the GPU, how do we protect it? How do we make sure that it's not intercepted? How do we make sure that you can trust the environment that you're running in? And that's effectively what confidential computing is for. It's a virtualization-based solution. You have a trusted execution environment. You can see kind of the TLDR of it just from the diagram here. The big news for CUDA 13 is that it's available for Blackwell. We have support for HGX B200. We have support for RTX Pro 6000. It's single GPU pass-through for now, so it's one GPU per trusted execution environment. That's expanding to multi-GPU pass-through and just a broader set of techniques and technologies in the future. This is really important for inference especially. It's not the full 8 GPU, but many times the full 8 GPU or the full cluster scale system is not required for inference workloads, especially edge inference workloads, and so this is pretty big. Finally, I mentioned Python back at the beginning. We've been putting a lot of effort into optimizing and building Python. And a lot of this is kind of along two axes. The first axis is how do we expose all of the richness of the CUDA ecosystem to Python without having you write C++ in Python? Nobody wants to do that. It's kind of counterintuitive or counterproductive. So what we're creating are multiple layers of exposure for the CUDA runtime, for CUDA accelerated algorithms. You can think about things like doing a reduction or a scan or element-wise operations, things like this in CCCL. You've always had optimized libraries on the C++ side. These layers bring you the richness of the driver API, the richness of the runtime API, and the accelerated algorithm libraries to Python, and give you a really nice way to program in Python directly. I'm not going to really go into depth about what all these things are. There are other sessions here at GTC I'll show you in a second where you can learn more about these. But if you go to the Accelerated Computing Hub, if you go to the documentation, if you go to our GitHub, you can find out all kinds of information about how these things work. A really big pain point for people too has been just Python packaging in general. There are lots of inefficiencies in the way that we were doing things. It was always kind of painful to install and do version management and so on. And some of that's really low-hanging fruit to clean up. And so the long story short is that we are cleaning it up. We've simplified the wheel name substantially. We took off the CUDA version tags, and now you just have one package that's versioned the way that the package managers expect them to be versioned effectively. We've also removed a lot of redundancy with the packaging in terms of removing and refactoring how we're installing things so that shared files are actually shared instead of having a single copy for each wheel that you install. Now they're shared as they should be. And we have a really nice and easy to use meta package that you can use with pip, where you can just pip install CUDA toolkit and you can select specific libraries, specific dependencies, a subset of the libraries. You can just request particular versions. And so our hope is that this makes installing things like PyTorch or other very complex applications much easier to work with. We're starting to roll this out, and we'd love any feedback that you have as you start using this, just to help us continue to refine this and continue to make this easier to use. So with that, I talked fast. I apologize for that. I did wind up with a couple minutes at the end, though, for questions. And we have other sessions on CUDA at GTC here. In particular, we have a session on CuPy Numeric, which is our large-scale cluster scaling out solution for Python. We have another session on scaling Python analytics with CuPy Numeric and Ligate Boost. We have training labs, we have Connect with the Experts, and a number of my colleagues are walking around both on the demo floor and just grab anybody with a green badge and ask them about CUDA, and we'll happily talk to you about it all day. So with that, I do think I have a couple of minutes for questions.
Thank you for the talk. I'm very excited about cache spillover into shared memory, so thanks for that. My question is complex data types in nickel. Is there any way we could get complex data types in the nickel library?
There's nothing that inherently prevents you from having complex data types in the nickel library. So that's not on the roadmap right now off the top of my head, but I can certainly take that back and we can work something in there.
Okay, thank you.
Thanks for the presentation. I work with Jetsons that don't have FP64 units, so I'm very interested in your extended floating point capabilities. But the Jetpacks versions always seem to be several versions behind the latest CUDA compilation. So will this thing work on Jetson AGX Orange? Is there a Jetpack for that? Or will the full 13.1 be on Jetson Thors?
Yeah, that's a good question. I didn't get into a lot of the details about this. Orin and Thor have fundamentally different architectures, and so there are different drivers. In terms of library support and enablement, everything that we're talking about will be enabled on Orin. The trick is that when I talk about unifying the driver architecture, that's for Thor and newer. So some of the things don't go back to Orin, and Orin will still have a little bit of a delay, but it's kind of one of my pet projects to make that delay as minimal as possible.
Okay, thank you.
Mm-hmm.
For new CUDA C++ programmers, the tutorials mentioned that you've been working on for a year and you're updating for 13.1 with tile specifically, so that's interesting portability. How do we find those?
There are two places you can find them. The first is the programming guide. If you just search for the if you do a Google search or something for the CUDA programming guide, that's being totally rewritten from the ground up. And so that's launching alongside 13.1. We also have two places you can look for CUDA learning material. One is a GitHub repository called the Accelerated Computing Hub.
Okay.
That's got a lot of the Python stuff in it. We're growing it out. And that's really where you'd go to find like tutorial material, right?
Okay.
How do I learn and just how do I get my bearings? The CUDA samples repository is equivalently being built up. That's much more reference material. How do I use this API? How to use that library? That sort of thing. So between those three places, that should probably cover you. And if there's anything that would help that we don't have, let me know, and I'd love to build it.
All right. Thank you.
Mm-hmm.
Quick question. You mentioned in the beginning talking about the programming languages that you're looking into C# as well. How deep will that go in this stack? Is it really for the SDK usage, or will that go beyond that?
Yeah, it's a good question. So in general, one of the things that I tend to believe, and you can all correct me if I'm wrong about this, I feel like if we're going to enable a programming language for CUDA, you should be able to do everything in that programming language. You should be able to write a CUDA, you should be able to write a kernel, you should have full access to all the libraries, you should have full access to, things like Cub and Thrust and so on. It should just be everything in the box expressed in that ecosystem. So we wouldn't do something piecemeal. If we're going to lean into a language, we're going to really lean into it and fully enable everything. There may be cases where that gets a little challenging at first. And I'll use Rust as an example here. Rust has, as part of its ethos, a real focus on memory safety. That memory safety and the memory model that Rust espouses doesn't really work at all with shared memory on a GPU. And so we're looking at things like, okay, if we did Rust, exposing tile programming in Rust is a relatively straightforward thing. And in fact, we'll have tile programming in Rust very soon after launch. If I look at how we're going to do GPU side general programming in Rust, do you want to write everything as an unsafe region? Do you need GPU safe or memory safe exposures of things on the GPU in addition to unsafe? How does that play out exactly? And so you may have situations with different languages where for kind of rubber meets the road reasons, you get things exposed at different rates. But our goal wouldn't be to just do a little bit. Like if we're going to do Rust, we want to do all of Rust. If we're going to do C#, we're going to do all of C# and so on. Mm-hmm. All right, I'm being told that they're about to get the hooks. So anyone who has any more questions for me, I'll be out in the hallway here for a few more minutes, or otherwise I'll look forward to talking to you on the floor. But thank you for coming. Really appreciate it.